Hi everyone, this is a video about the variance of predicted values for ordinary least squares regression, or simply just least squares regression. And I'm going to show you two different ways on how to think about calculating the variance of a predicted value. I'm going to start off with my favorite way, and then I'm going to show you another way that I'm not so fond of. So first off, let's just talk about our setup of what's going on. Right now we have the dependent variable y, which is an n by 1 vector, and we are assuming it's normally distributed with mean x times beta, where beta is a p by 1 vector and x is an n by p matrix. And we are also assuming that there is standard deviation, which is sigma squared times the identity matrix, and that is n by n. In this case, that beta vector includes beta naught. P is the number of coefficients, and then n is the number of observations. We also, I'm not going to derive it in this video, but beta hat is the formula x transpose x inverse x transpose y. And again, y is a vector of values. We have a fitted value yi, which is defined as xi times beta hat. Beta hat is the estimators of the beta vector, and xi is a 1 by p vector. So this is our setup, our home base, just a general setup for the problem. So we have variance of yi hat is our desired value. Variance of yi hat is defined as xi times beta hat. This is by definition of yi hat. We then can substitute the beta hat values in terms of x's and y's. So variance xi bar times x transpose x inverse x transpose y bar. This is by definition of beta hat. X's in this case are observed or known values, so they're actually constant and we can pull them out. Recall your variance rules. When you pull out a constant, you actually square it. But since we're using vector notation and linear algebra, we're going to have to manipulate the problem a little bit. So I'm going to pull out values, xi times x transpose x inverse times x transpose variance of y bar times x transpose x inverse xi bar transpose. And then this is by variance and linear algebra rules. So if you're confused on the linear algebra, I would look up rules regarding transposes and inverses. Next, we have that. So let's plug in the variance of yi, or y bar, because that is a known value that's part of our assumptions. We know what that is. It's sigma squared times the identity matrix. So I'm going to go ahead and do xi bar, x transpose x, inverse x transpose. This is sigma squared times the identity matrix times x transpose x, inverse xi bar transpose. And this is, we are able to do this by y bar assumptions. It's what we assumed in the beginning. Sigma squared is just a constant, so we can move that around. It's not a vector, it's not a matrix, so by linear algebra rules, we can just move it over here. Xi bar, X transpose X, inverse X transpose. Next thing I want to show you, so we've moved sigma squared. This over here is n by n, and this X matrix is n by p. This whole guy just becomes X. And again, look up linear algebra rules to see why that's true. Now we have X transpose X inverse X bar I transpose. We got here by linear algebra rules. Now let's see, we can simplify this a little bit more. So here is a square matrix inverse times the square matrix where it's not an inverse. And we know for two square matrices, A inverse times A is actually equal to an identity matrix. So we can use the same property as before and kind of break this down. They in a sense cancel each other out. Again, please look up linear algebra rules if you find this part confusing. X transpose X inverse. So these two basically cancel each other out. So this comes down here, the X transpose X inverse, and then we have X bar I transpose. We can't simplify this any further. This is our desired result, the variance of y I hat. Another cool property, just a little side note, not the focus of the video. Note, if we were calculating the variance of all fitted values, this would actually result in sigma squared X transpose X inverse times X, which is equal to sigma squared times the hat matrix. It's kind of a cool property. I'm going to let you figure that out on your own. Last thing I want to do really quickly is show you how some introductory stat courses kind of introduce this topic. They typically do like a variance y I hat, and I'm going to do this for simple linear regression. Y I hat is equal to beta naught, beta 1, xi1. So they substituted in beta naught hat plus beta 1 hat xi1, and then they break it up, variance beta naught hat plus variance beta 1 hat times xi1 squared plus 2 times xi1 covariance, and then this is beta naught hat, beta 1 hat. So some people will do this as the variance of y I hat. I don't think this is the most helpful way to introduce this topic, because it kind of makes it look like these beta values are random variables, but they're not. They're functions of our data. They're functions of the x's and the y's. And the x's and the y's are the variables. And the y's have the assumptions, they have a variance. And so we always want to go back to a home base in terms of x's and y's, or x's and epsilons, because that's where all of our assumptions lie. And so you can calculate these individual variances totally fine, and in another video I do that. I don't think it's the most helpful thing to write it in terms of this though. Anyways, just wanted to throw it out there because you do see it written this way. I still think it's helpful to boil it all the way down to x's and y's though. Okay, that's it. Please let me know any questions, comments, and concerns. I'm always looking to improve my videos, so don't be shy. Thank you.